It's Friday the 5th of February 2021 and it's 7:45 in the morning. I'm in West Cork, Ireland, in the as dawn is coming up, and I am going to talk about building fabric. What do I mean by fabric? And some of the explorations I've had in terms of fabric over the years. I suppose my background is an electrical engineer, so I don't have a academic history in learning about fabric. But one of my first jobs when I became an academic in 2009 was to teach on a module that had half of it was in services and half was in materials. So we brought guest lecturers in to do the material sections, but I became fascinated with various aspects of different types of materials. So I've spent time exploring different, I think probably the first one was bricks and the tradition of bricks. Different parts of the British countryside would have had its own type of local brick depending on the type of clay they would have gotten. And then I would have looked into how it became the traditional building material of Britain from the time of Henry VIII and Hampton Court, which is probably the most famous brick palace, to the brick countrysides and street views that were traditional in the northern mining towns, so on and so forth, each of which would have had its own kind of traditional element. That was interesting. I suppose from a technical point of view, I became more fascinated with actually the moisture absorption of bricks, that you can get different forms of bricks that absorb water at different rates, and that becomes very important because it's your facing material, facing outside, and you're going to get freeze-thaw action on the surface. So a brick's ability to resist water absorption is actually a sign of quality. That's the one thing I remember from my years, quite a number of years ago now, and my colleague Danny now does that teaching for me. And any of you who will have seen his modules will know he gets equally excited about bricks when he's trying to teach it to you. Then I would have explored concrete. Concrete went from being this boring grey material that seems to be around us everywhere to something like baking, the great British concrete mixing, because you can have so many different types of materials, such different quality between the different types of materials, how they're blended together, in what proportion, and they give you all the whole huge range of different types of concrete on the other side, from the cheap nasty stuff that you build walls in your garden out of to the highest grade stuff that you build the Severn Bridge out of. And there's such a huge difference between them all, and it gives you such great output. And really, we don't talk about stone because we don't use cut stone anymore so much in construction, because we have liquid stone. Liquid stone is concrete. You build a mold, you pour the liquid into it, it goes hard, and it's harder. It's as hard, or if not harder, than most stones that you could build out of. It's a wondrous material, really, except for the unfortunate fact that it's hugely environmentally destructive, not just in the fact that it takes energy to make, but as a byproduct of making it, carbon dioxide is also emitted. So really, becoming lean and frugal with your concrete use is one of the things that we should aim for in our construction. Then I explored timber. I probably had a fascination with timber going back a long time, because actually my family business was in a timber merchant. Even though I would never worked in it that much myself, I did spend occasional summers putting down hardwood floors and target flooring, things like that. But my exploration on the academic side became to do with the strength to weight ratio. The reason why we use Scandinavian timber as opposed to British timber is because it's much more dense. They have a slower growing season. Rings are close together, more dense, stronger for the weight. Traditional old buildings used to just have to have huge timbers. You go up to a 13th century building or a Tudor building, they had massive big timbers to hold up the roof. Nowadays, much leaner timbers holding up the same weight because we've engineered better timbers. Probably I have a lecture I give on the sustainability benchmarks, and I use timber as a good example because there's actually really exploring sustainability in timber and how timber is grown and how it's places in the world where it's grown responsibly and places in the world where it's not, and you really learn about that type of the processes that are in place to try and encourage manufacturers of materials to be more sustainable. It's a really nice little case study. I really disappeared down that rabbit hole for a few months as I researched the sustainability processes that have gone into to timber over the years. And then I would have looked at metals as well. So steel principally, iron, going back to the history of wrought iron and cast iron, and how eventually it led to the discovery of steel, and just how wondrous steel is in terms of how much further ahead it is of any other material when it comes to strength, particularly tensile strength, the ability to hold things together rather than the other types of strength. So again, I kind of got lost on that. But what really emerged at the end of this process, and what I then used to teach at the end of that session, was that you start, once you've studied materials enough, they stop becoming materials and they start becoming elements. So you have a wall element or a ceiling element or a floor element, and that element starts to have properties. So you say, well, I need my wall to be this strength, and I need my wall to have these other functions. And then you go away and you start to look for the materials that can meet that purpose. So you might go with an emerging material, something like straw bale, but you realize that it doesn't have the same properties as what you're replacing it for. So you have to put layers in there, or you have to run it a certain way, or you have to have an expectation of a certain amount of maintenance every year in order for it to perform in a similar way. Because as an element design, it needs to be a composite. It needs to be a number of layers to give you the overall function. And that's where building designers eventually get to. They stop thinking in terms of a material, that you're like a concrete or a timber or whatever, and they start to think of a building as an element, and that element has performance. And that leads us nicely onto the definition really of fabric. Fabric isn't just about materials. Fabric is about the layers of a building that has a function to it. So the inherent in our understanding of fabric is that it's not just the materials that it's made of, but it's that material has a certain amount of function. And particularly, you think about similar to clothes that we wear layers of clothes. Most walls nowadays have layers in them. They have internal layers throughout the middle, and an external layer. And all of those layers are in there for a certain purpose, certain functions, certain outcomes that they wish to achieve. And those functions are what I'm going to go through in the rest of this little musing podcast, and think about how different materials and different layers, and when we're thinking about fabric, what are those things that we're trying to get our building fabric to do. So if I just think of a typical wall now, for example, I might say a wall has a insulative function. So it provides insulation to keep a temperature difference either side of it to a certain level. Now that wall may include the actual middle of the wall itself, which has insulation behind it. It may include windows, so that layer I'm considering also includes the windows. It may include gaps, the junction between windows and walls, where you're going to get no insulation but solid timber framing, things we call thermal bridges, and it would include those. It may even include areas where there's a cable going through the wall to a light outside, and there's air can get in around that cable. So little gaps and little holes in around that air can go through, that may include those as well. So again, it's not just that the material, one material that the wall is made of, but it's all the different materials, including things like windows, also the functions of the junctions, and things like little gaps here and there, they all contribute to the function of the wall. Hence, they're all part of the fabric that we're thinking of when we say the word building fabric. So if you want to know what we mean by the term building fabric, it's more than just the materials or the structure that we're using, but it's inherently the layers of a building that give us a certain function. So hopefully you have some understanding of that. I'm going to go through the different functions of a building fabric now, some more detailed than others. I've tried to do all of them. Some of them are relatively minor and some of them are major when it comes to the design of zero carbon buildings. But I'm going to try and muse about all of them. And maybe I've missed one. Maybe you might be able to identify one that I have not thought of. I'd be interested to know, and I'll add for other people to think about. So the first one, obviously, is that a fabric needs to have strength. Now, there are two ways, of course, for a building to really be, well, more than two, but there's the two principal ways of a building being held up, and that's that the weight of your roof and the other floors are held by the walls, the external walls. So in that case, what we have is that the fabric itself needs to have strength properties, and I won't go into that. That's kind of civil engineering, structural engineering, but obviously for all the different types of predicted outcomes in the building, whether it's wind strength, wind pressure, or whether it's earthquake in some parts of the world, or just general wear and tear and weight that you get, the walls would have to be strong enough to hold up the building. Now, perhaps it's not a structural wall, but you have actually just an internal frame, like a steel frame, and you're just hanging the wall out of it, like what they call a curtain wall. It doesn't have to have that much strength property, it just has to hold itself up, really. And it doesn't need to have any role in holding up the roof, so it's called a curtain wall for that reason. Works a bit like a curtain, and now the wall of the function is kind of freed up from just having to provide strength to also to just concentrate on the other functions that we need from our wall. So that's strength. I'm not going to go into strength too much, but I could do. I'm sure there's some people out there who are teaching all about the strength aspects of wall and the various types of strength. So your tension, compression, bending strength, moments of turn, all those kind of things that you need in terms of a strong wall. I'm not going to go through any of that. The other really obvious one, that the function of a wall is to keep out the wind and the rain, to provide shelter. Our very first buildings were just wraps around fireplaces. We wanted to create a nice internal environment, comfortable environment for all the different types of places that we migrated around the world. So we brought the fire with us, we brought the house with us, and as we hunted and gathered around and chased various herds of animals in ancient times, and they still do that in some parts of the world, at night time or whenever we decided to move on, we'd set up a fire and we'd wrap a canvas around it, and we'd create a different internal environment. So keep out the wind, keep out the rain or the snow, and make sure that we're comfortable. And obviously that a building that fails to do that is a failure, no matter with zero carbon or not. And because we've lived in 100 years of free, cheap energy, we've lost a lot of contact with the other functions of our buildings, but this particular one isn't one we can compensate with just loads of energy. So it's still something that tends to be a very highly skilled activity that architects and designers do, is the prevention of water getting into a building or wind getting into a building and causing drafts. These are things that we're very good and very adept at still doing, and it's a high skill, because it's obvious when we go wrong. People are uncomfortable in drafty houses. Dampness forms and mold grows, and buildings erode and rust very quickly if water gets in. So we're quite good at that. So I'm not going to go into that in too much detail. It's the other things that a wall does, or fabric does, which we can compensate by just racking up the energy, which we've kind of lost contact with. And we kind of have to get back to being as skilled at these other things as we still are with keeping out water, keeping out wind, when it comes to the function of the fabric of our building. But the first real and probably the most important function of fabric from the point of view of living in the UK is the fabric's ability to retain heat inside the space. So most of it, we live in quite a mild winter or summer climate. We don't overheat too much. We don't have to live in air conditioning. I've been in Hong Kong during the summer the last few years, and trust me, you just go from building with air conditioning to air conditioning. That's what you're looking for, and you spend 10 minutes outside of that environment, you're very quickly looking for it again. So we don't have that kind of environment here in the UK. So principally our buildings are heated buildings. In the wintertime, we have the boundary between outside and inside, and we heat the inside to the temperature that's comfortable for us, between 18 and 22 degrees. And so the wall's job is to keep that heat in. And now this is the number one function when it comes to zero carbon buildings that the fabric has, is especially in this part of the world, is during the winter time, keeping the heat in and not losing it quickly. And so we need to put some form of insulation layer or insulative properties in the materials that we choose for that. By far the best insulator is actually air. Air is a fantastic insulator. It doesn't allow heat to transmit through it very easily. However, it has that function, as we discovered in the last lecture, of when you heat it, it rises. So if you could somehow freeze air and hold it without moving, then it becomes a fantastic insulator. And that's what most insulators are. If you have a jumper on right now, it's probably a puffy jumper. Why is it puffy? Because it's holding lots of air inside of it. It has lots of weaves. And it's actually the air that's keeping you warm right now, that's not being allowed to move, that's inside your puffy jacket or puffy jumper. Right? It's the air that's insulating you. So if you've ever seen insulation material, you know it looks a bit like that. It's big puffy material, and that's how it's holding air in position, and that air then is giving you fantastic insulative properties. We'll examine different types of insulation in the workshop. Will range from the two major industries that provides industrial insulation. So the petrochemical industry provides us with polystyrene insulation, and the glass industry provides us with rock wool insulation or fiberglass installation. And then you have a range of natural insulations that are emerging or re-emerging again, although it's always difficult to scale them up. So we'll discuss them in more detail during the workshop. I won't go through into them there. Again, it's another rabbit hole I disappeared down for a few weeks, quite a number of years ago, and quite interesting to see all the different types of alternatives out there, what people are trying to do to give you insulative properties. And of course, there's a huge area for debate now, because we were so busy insulating our buildings for the last decade that they kind of ran away with it in those tower blocks, and they put insulation in that was combustible, and we had that huge tragedy in Grenfell fireplace, the Grenfell tower at least, where it went on fire, and that was the insulation that was primarily burning. So they were trying to do it for energy efficiency reasons, but they lost track of other properties, and that's a recurring theme. If you focus too much on one aspect of a building and forget about the other aspects of a building, you lose track of it. That's why architects spend so much time designing, years designing, is because they have to keep all of these different perspectives in their thought. So in terms of keeping heat in, I like to think actually that a useful mindset of how your building fabric keeps heat in is to think about heat as what it is, the vibration of air molecules at a molecular level. So if you have heat inside of a space, 22 degrees, then that air is vibrating quite a lot. But if it's cold winter's morning like it is here, outside of the door, it's maybe 2 degrees, then it's not vibrating out there. And you know, every time you throw a stone into a pond and you see that nature, the water disturbs one place, but eventually it pans out and evens out, that nature likes to even out. So all the vibrations in here want to work their way out through your building in the easiest way possible to get out, to make sure everything is calm. And if we don't keep injecting heat into the inside here somehow, then we turn off all the heat sources, then it will vibrate its way out, and eventually the vibrations both internally and externally will come into balance. Because nature wants that, likes to have a balance like that. And I think if you think then of heat vibrating its way out through your fabric during a winter's day, then you get a really good sense of what a thermal bridge is. It's that part of the wall that vibrates really easily. It's the metal that goes through the wall, through the insulation, and the vibrations easily make their way through that little bit of metal, even though they find it hard to make their way through the air in the middle of the insulation wall. So when we start talking about eliminating thermal bridges and detailing our buildings so that we don't we maintain the insulative layer in there, it's because we want to slow the path of this vibration, this energy making its way through our wall. Likewise, windows, even the best windows are still 10 times worse than a wall at keeping heat in. And this is a really big issue with modern buildings. Modern designers love using windows more and more in glass. If you were to chart the average percentage of a facade that has been glazing, it has been an ever increasing percentage since just about the day we started using glass in buildings. Over the last 400 years, if you were to chart the average size of total percentage of a facade as glazing, there are some buildings now that are 100%, but the average would be higher and higher and higher. We just seem to love more and more windows and more glazing. But even the best window is 10 times worse at holding heat in than a really good wall. So actually, zero carbon buildings, if you look at all the examples that are out there, and there's plenty of examples out there now, glazing is no more than about 25% of the facade. And even then, that 25% is probably triple glazing, and it's probably facing south so that you're getting free heat during the summer. You're kind of mining the sun, so you've oversized the windows on the south side of the facade a little bit in order to gain that passive heat we'll be talking about in the session about solar. So we're going to talk a lot about and the technical lecture will be going into discussing the ability of a wall to keep heat in, something called U value for most of the wall. And those of you who've studied this before, that term will be very familiar with it. The reason why it's so familiar is because the UK government has used U value since the early 1980s as the metric by which they would mandate performance. So they have made it a rule that your U value has to be a certain level, and they've been making that level better and better and better as the years go through to make the buildings more insulative. So it's kind of like the rules are set up that the U value has to be a certain level, and so that's why it registers high on architects' minds, even if they don't know how to do the calculation. They know that U value is really important because it's the metric that's used to measure the insulative properties of a wall. U value is not the only value, though. We have two others. We have the lambda value, which is a representation of linear thermal bridges, like the lintel under a window. So the lintel under a window, that thermal bridge is measured as a lambda value, and then your point thermal bridges is at junctions is measured as psi values. And those of you who get into passive house design will know that psi values are used as a tool to ensure that you are detailing to the correct level of sophistication. There is a process there for calculating the psi value, the heat lost at corners and junctions, and the whole point of focusing on that as a particular tool is to ensure that you are detailing correctly. That's the metric they are using to ensure that you are detailing to the correct standard. But they all pretty much are related. The U value, the lambda value, and the psi value, they're all related. They all just have to do with how much heat goes from the inside of your building to the outside of the building, how easy it finds that movement through the process of conduction, the movement of heat through solid materials. Okay, so that's going to be the major technical consideration for fabric that we'll think about. But Fabric has other functions, and again, this is part of the thing is having to think about all these other functions, and then realizing that not only do we have to make sure the fabric does them all, but they're all interrelated, and you focus too much on one, and the other one will. It's a bit like that what's the game with the moles that pop up, and every time a mole pops up, you hit it on the head with a hammer, and then the other mole pops up, and it's like you think you have everything down, and another one pops up somewhere else. It's a bit like that when you're designing fabric, is that you're trying to balance all these things in, and you realize, oh no, the fire regulations is all out of whack because I've been focusing too much on energy or whatever it is. That's all part of the parcel of being a designer. It's an iterative process. You have to go around and around and around, thinking about all the different perspectives and try to find the best balance. Another function of building fabric is what we call using the fabric as an energy store. So this is a term called thermal mass. We're going to explore this more under the solar section when we talk about passive solar design. But suffice it to say that if you have a material that's inside your insulation, and that's very important, has to sit with inside your insulation, then you can use that as a thermal store. So if you heat up that layer, it takes a while to heat it up. It need only be around 25 mil thick, because that's about the most that would heat over the course of a day. And then it can give. So if you had free energy, for example, during the daytime from the sun, you could heat up your internal mass, thermal mass, and then during the nighttime that mass will slowly release back into the building again. So you're using the thermal mass as a store. So it needs to have certain properties. It needs to have a moderate conductivity, so not as conductive as metals, more conductive than timber. So something like the best one is actually water. The water is by far the best, but we don't like to build our buildings out of water. There's functional reasons for that. But concrete's pretty good, or bricks are pretty good, or heavy exposed materials, stone is pretty good, slate is pretty good. The other property you have to have is a high specific heat capacity, so a high ability to be a store, how much energy it can actually hold. So high capacity and moderate conductivity, those are the properties of a good thermal mass. And then it has to be in contact with the internal layer, so it has to, air at least. So it sits within your insulation and has to be in contact with the air as it moves around. And you see various buildings like R Block on our campus. They've been designed with a heavy thermal mass philosophy. They got some things wrong in R1. They've done slightly better in R2. And I'll go through that in much more detail in the session on solar. But that's another function of our building, could be to add mass as a lightweight or a heavyweight. These are terms we use in terms of its thermal mass, thermal weight, relative to performance as using it as a energy store to maximize the use of free energy such as the sun. Then, of course, the building fabric needs to also work during the summer to keep the heat out. So now we have a hot summer, it's really hot outside, and we want nice cool buildings inside to keep us cool. We don't like going over 25 degrees, most of us. We might be happy up to 28 degrees. We definitely don't want over 30 degrees. In fact, there are rules set for certain buildings like schools that say you shall only go over 28 degrees for 130 hours a year, and you should never go over 30 degrees. And so actually that's the performance criteria set for things like schools, and then we have to do a lot of modeling to see how a building would actually perform to make those kind of standards. That's a typical stage 1 design criteria that would be set for a design team to achieve, and they start their design then in stage 2. But keeping the heat out and over is to ask the same building fabric to do that's hard. I mean, you imagine you don't wear winter clothes during the summer, right? You have summer clothes for the summer, you have winter clothes for the winter. In fact, buildings used to work a lot like that. We used to have winterize our buildings, and we used to, even not just winterize, but have a big difference between night and day. When we had, especially these big old buildings, I enjoy going to the kind of National Trust buildings and going around and seeing how they worked. And one thing that strikes me is that the conservationists conserved the materials, but they didn't conserve all the actions that would have happened to change those materials between different times of the day and different times of the year. And there's a very practical reason for it. Originally, those buildings would have had tens upon tens of indentured servants going around to close your shutters or pull your drapes or hang your tapestries in the winter time, or whatever it is you do to change that fabric, alter that fabric to make it better at keeping the heat out during the summer. Or I one of the ideas I've thrown around with the society has been, let's try to start a tradition that every September we have a weekend where everyone thinks about winterizing their house, or a weekend in May where everyone thinks about getting their house ready for the summer, and it could be things like hanging heavier curtains, because that again changes your fabric around windows. So at nighttime you're changing your curtains, or fitting better your draft proofing, or whatever it is you do to manipulate that fabric to make it perform better. But typically, most buildings nowadays, we don't change them that much between summer and winter, and the fabric has to do both jobs, which is not an easy thing to do. So how do we keep heat out? Well, first of all, it's there's three primary sources of heat getting into a building. One is the machinery in the building. The other is the people in the building. Those two things are hard to change. And the other one is sunlight. So we can get rid of sunlight, and we can shade and keep that out. And we'll talk a lot more about that in solar. That's the principal one. We can really look at the technology of our glass to see the type of glass that we have. Will it work well at because the type of energy that leaves during the winter time, the heat that goes through that glass is long wave radiation, whereas the solar energy that wants to come into that glass, if it's a south facing window, is short wave radiation. So we can actually have glass technology that reflects more of the short wave and transmits more of the long wave, and so it's good at keeping heat out. Or keeping heat in, but maybe also keeping the sunlight out. So there's various technologies there, and I'll explore that in a podcast about glass too, which I was thinking of doing as part of this one, but now I think I might leave it as a separate one, because it's going to run a lot of time as it is. The other thing about keeping energy out, the insulation that you've put in your wall for winter time will also play a role in keeping that building cool, especially if you have artificial cooling. So if you have air conditioning or some form of artificial cooling in your space, now you like that insulation just as much, because you don't want to lose that energy out, and you're almost in a reverse scenario as you would be in summertime. And most of us don't have in wintertime, most of us don't have artificial cooling in our houses. It's quite common in offices, but not in our houses. And so the way of cooling in this part of the world, is actually just to open our windows and increase ventilation and make our fabric more air open to the movement of air through it. And we might even put a fan in our building to the very hottest days to accelerate that air, because the movement of air gives us a cooling effect. So again, our fabric becomes openable and in order to allow for cooling. The very last thing I want to say about keeping heat out during the summer is the external layer of your fabric. That's going to, especially on the south side of your buildings, that's going to really be at the forefront of being hit by the sun, and anything that's hit by any fabric that's hit directly by the sun is going to be worn down by that intense shortwave radiation, the UV radiation, and you're going to get a large difference in temperatures very, very quickly on the very first couple of millimeters of that surface. So it's got to be a pretty tough surface to resist that really high increase of temperature that happens when you get direct sunlight hitting it. So that has a role when we talk about radiation a bit more as well, in keeping the heat out. So that's three kind of heat-related functions of our fabric: keeping heat in, working as a thermal store, and then keeping out the heat during the summer. One other thing I want to talk about in terms of relationships too is that external surface. Not only is it get direct hit by sunlight and gets these kind of thermal shocks that we call right in the first few millimeters, but also, as I mentioned about the bricks, if that surface becomes some way permeable to water, then you can get freeze-thaw action, which is the biggest form of how buildings fail in terms of the external surface. So freeze-thaw is that the water, like today, is frozen. It expands, it pushes all the cracks and pores that it was in apart, and then when it thaws again, that external surface has been eroded. So you see quite a few old walls that have been eroded by freeze-thaw, and the whole external surface is just falling apart. And so that's why, modern buildings, things like concrete, are just fantastic at resisting that kind of stuff. Or we may put layers of paint or layers of there's an external surface treatment, and most of the time it is to absorb that heat shock and resist freeze-thaw. So the external surface of our fabric plays a significant role in how that building not just looks, but how that building actually works. Another big area for fabric and the function of fabric is a term we call airtightness. In fact, zero carbon buildings, if you want to think of the two big things we need to design for zero carbon buildings, it's insulation and airtightness. Think of that word. Write those words down if you're writing that, and underline them. What are the focus of zero carbon buildings? Insulation, underline, underline, underline. Airtightness, underline, underline, underline. Airtight. What do we mean by airtightness? I don't like the idea of being in a building that can't let air in. That sounds suffocating. Is that a good thing? To have a suffocating building? And it's not, obviously, but in a zero carbon building, we control the ventilation. Okay, so there's a difference between controlled ventilation and leakiness. Leakiness, or to give it a technical term, infiltration. Infiltration is uncontrolled leakiness, right? I have things in my house that control ventilation. There's vents, there's extractor fans and tubes. There's windows that open, there's doors that open. All those things I can control. I can close them. I can stop the ventilation from going out if I wish. If I want to be in control, I can turn off a machine, a mechanical ventilator. I can close a window. I can close the vents. So I can control those items, but imagine I closed all those items and they're all sealed. There's still a lot of ways air can get in and out of a building, especially old leaky buildings. It's the leakiness, and they're through places that we don't particularly think of as where air goes through. So there might be the gaps in walls, especially around windows, around doors, at junctions where internal floors meet the walls, or at any floor meet the walls, or where the roof meets the walls. You're going to get air going through, and you can test this. We do an air tightness test. We pressurize the inside of the building by pumping air into it, and we see how much energy it takes to maintain a 50 Pascal difference between inside and outside. And there are some buildings that are so leaky, even though we've closed all the windows and all the vents, that it's almost impossible to keep that very pressure difference. And so as quickly as you're pumping air into the building, it's nearly getting out again, so in and around the leakiness. But a really, really big focus of high performance zero carbon buildings is eliminating all of that leakiness as much as possible. So that's what a lot of the detailing is in building fabric, is that they're thinking of the air barrier, the way that fabric can hold in and get rid of the leakiness, and then we control where the air goes in and out. And so a lot of the detailing in around windows, around doors, even things like letterboxes and cat flaps, you can get passive house rated letterboxes. They're not very postman friendly, but they still work. You can get passive house rated letterboxes, because that could be cat flaps, because that could be somewhere where air comes in. You want to eliminate that. That's not its function. And so all the items of a building, you're trying to eliminate the air intake of that, or the air leakiness of that as much as you can. So that's a big focus of zero carbon buildings is the air tightness, and it has a significant impact on the design of the building. This becomes it's easier with some structures. So if you're building a concrete building with plaster inside, then actually that material itself, the two layers of the cavity wall and the plaster, it's a pretty good seal system as it is. You probably just have to think about the junctions between the floors and that wall. Make sure it's hanging inside rather than going through the wall, that kind of thing, to eliminate the thermal bridges. However, if you're building out of timber, it becomes an altogether more complicated process. If you have a timber stud work and you're putting plasterboard on it, you probably have a layer of plastic in there that's called the airtightness membrane. It's a whole layer of plastic that's role is to stop air going through from one side to the other. And you not only put the layer of plastic in there, but then you have to tape it. Tape all the junctions, tape all the joints, tape around any penetrations like the windows or any pipes or any cables that are going through it. And let's just say the people who I've seen who are passionate about designing their own buildings, they might get a builder in to do a lot of the work, but that taping at the end and inspection of that taping, they normally do themselves because they don't trust the builder to not, hammer a few nails through the fantastic membrane that you're putting in the middle of your wall. Even when you're putting a nail through it, you want to make sure that nail is sealed and it doesn't cause a leakiness in it. So, that it becomes more complicated in things like timber structures that air barrier. You should look up some videos on YouTube to see how air barriers are put into timber buildings. It becomes a more difficult process. It's just the movement of air through the fabric in places that it's not supposed to be. Eliminating that and making your structure airtight. Very closely related to air tightness, but fundamentally different, is the idea of breathability. Now, you might think breathability is a term that refers to air tightness, the movement of air, breathing air, that makes sense. But actually, it's more complicated because we're not just thinking about the movement of air, we're thinking about the movement of water vapor. And that's why we have a whole section on water, is because it's actually water vapor, the gaseous form of water, and how it moves through spaces. And you may have to think, and actually that where zero carbon buildings go wrong, where zero carbon buildings fail, is normally in poor condensation, poor control of water. There's nothing worse than after a couple of years of a zero carbon building, you start to get damp patches everywhere, mold growth, and a failed building because you didn't think about the water and the vapor. It is the thing that will get you if you don't think about it very carefully. So we have to think about the movement of water vapor and moisture and the risk of condensation on and in our walls and in our fabric to a very great detail. And it is really the hardest part for me controlling especially in old buildings, is what is the water going to do in your building? Is it going to come back and bite us and ultimately be a failure of our building? Great thing about concrete is that it's not really an issue with concrete, and concrete's so tough it kind of resists it even if it does become an issue. That's why cavity concrete walls are just like, they're cheap and they do the job and they're just frustratingly good at it, Whereas if we start to look at timber structures and we already have a layer of plastic for air tightness, we may now have to have an air of plastic also for membrane water control. How might have to be a separate. Now, sometimes you can get one layer that can do both, but when you look into the details of what parts of the structure is the best place to put the layer, often the vapor membrane really needs to go on the inside surface of the insulation. It wants to be where it's warm, right? So just behind your plasterboard, just before the insulation, that's where you want your vapor membrane. But often the air tightness membrane is far easier to put on the outside of the wall, just behind the external surface. So, sometimes for practical purposes, you end up having 2 full layers of plastic in your wall or in your roof to try and control, one to control air tightness and the other to control the movement of vapor. Again, we'll explore that more in the session on water, where we think a lot more about keeping the control of water vapor through our wall. So that's probably the hardest thing to control, particularly on old buildings. Since the 1920s, most buildings in the UK, houses in the UK, have been built with a cavity wall. But you go older than that, you start to have solid walls, and they can be, up to 1 meter thick. And we've kind of forgotten how to actually design for solid walls. They're very, very subtle. They still do their job, but they require a certain amount of movement of moisture all at one time through that wall. It kind of works. Those walls work well if there's a very, very slow movement of air and moisture through them at a constant rate. You can actually over-insulate old solid walls. You can put too much insulation on them and they can start to form dampness problems and start to crumble very quickly. So it's almost counterintuitive. You might think, I just have to improve the U value. I'll put a whole load of more insulation on my walls and hey presto, internal insulation or external insulation or whatever it is, and I've saved the planet. 2 years later, your building's falling down. You're going, what's gone wrong? Oh, I didn't really understand how that old wall worked and I've over-insulated it, and, we didn't get an expert in, a zero-carbon expert. And probably the most expensive zero-carbon expert you may ever have to hire will be the person who is good at solid walls and where you should put your insulation, and they'll come in and do analysis because you don't know what's in the middle of that wall. That's the hardest part, is that, back in the 1800s when they were making that wall, they were filling the middle of it with all sorts of crap. So trying to predict what's in there and what the moisture will do as it's moving through there is one of the harder aspects of trying to retrofit old buildings, which is far harder than building new buildings, but probably more important because there's a lot of buildings already in existence. So that's breathability or vapor membrane, control of the vapor as it goes through. The only other thing I think of as for building fabric function is the internal color. Obviously, just for aesthetics, you want a pleasant wall and a wall that's good to look at and brightness. But also, it plays a role in general need for less daylight. If you have internal bright surfaces, then the light travels further in from the windows, so you don't need electric light as much. And generally the internal surface color is another important aspect of your fabric. So those are the different functions I can think of a building fabric in terms of external layers of a building, the bits that separate the outside environment to the inside environment. And if you can think of any others that I haven't touched on, then I'd be delighted to hear what you think. Let's just see, was there anything else? Yes, I think maybe we need to think about more in zero carbon buildings, not just about better designed, but that idea of adaptability, that we do winterize and summerize our buildings, and that we do take a weekend to appreciate, put up heavier curtains, or or if it's coming to summertime that you're, passive houses, you don't want to overheat, so you're maybe putting on shades, putting on for the keep the sun out that you don't want to have on all the time, or you're opening up vents that would only are only there for winter summertime use, or something that's that idea of adaptability. The idea of thinking about materials. When you start investigating materials, you get lost in the actual individual materials, but as you study their use, you start to stop thinking about materials and start thinking of layers and layers with fabric and functions. So that an element with layers that have a function should be where you start with in the end. It should be that you identify the external surface of your building. You say what kind of strength and what kind of air tightness and what kind of insulation layers you should have. And then you go away and you say, all right, now I want to base it on straw bale or bamboo or clay brick, something unusual maybe. But now you're thinking, okay, but in order to meet my performance of my element, I'm going to need layers with that. I'm going to need the external surfaces to do something. I need the internal surfaces to do things. I need to think about air tightness, insulation, and permeability as well. Permeability being the technical term for vapor control. So that's important. I'm going to do a whole other session on glass. We've talked about the vibrating heat. Yes, I think that's most of it really. What I'm going to end on my exploration of materials as well is the idea I hear sometimes when it comes to sustainability that people jump to the easiest solution. So they might go, oh, they have to be locally sourced materials, and I'm always a bit uncomfortable by that being the criteria we set for building materials. Locally is tradition, certainly. I mean, the history of the world is that more complex societies can move bulk goods around rather than just luxury goods, and so we have got a planet now where we have an incredibly efficient transportation system, and it may well quite be true that even if you live down the road from a steel plant, that steel plant might be so old and dirty and subsidized by a government that it's actually the worst steel you could get, and you're far better getting that steel from the other side of the world, even though you have to ship it in because the factory is just so much newer and cleaner. So I don't subscribe to the local is better tick box. I would do a proper evaluation, a life cycle evaluation that includes manufacturing and transportation, and I have to look at it all in balance. So, okay, and it's a different argument if you want to use a material because it has a local tradition. That's a better argument for me, rather than saying, oh, for sustainability reasons, we have to use local materials. For me, that's not a very well thought out argument. And normally the people who make that kind of argument, when I talk to them, they don't know anything about life cycle and they don't know about all the techniques that we have for actually measuring the life cycle embodied carbon of a material. And it's very good to hear that we're doing a lot more on embodied carbon now, and that is going to emerge as the main metric for evaluating the sustainability of where we get our materials from. So I just wanted to end it a little bit on that one as well. We're not going to cover too much on embodied energy in this course. This is really about the zero carbon skill course is about operational energy and zero carbon on operational buildings like Passive House, and understanding the different aspects from that point of view. So I have carried on now for 52 minutes. I've enjoyed this, and I hope that it has made sense to you. This was my first draft of it. I was thinking in my head I'll do 3 drafts because I'll mix up what I want to say, but I actually think it's been pretty okay. So I might actually just issue this out as it is, first draft and all. But that means I might do a better podcast for future sessions. So please be critical, especially if you're a student in your level 3 modules. You should have a more critical friend now and come back and correct me on bits, or say what I should have said, or add things I should have added, or things I should have taken away. Be a good critical friend now and come back and tell me what you think. Tell me what I should have added or take away for future uses. I need you as a sounding board, a crowdsourced sounding board, to be as good as we can be, so that this whole framework we're putting in place, which I really wanted to have a student run, is self-perpetuating in years to come. So I'm now going to go have my breakfast and perhaps a walk, because it's looking like it's going to be a very nice yet cold day. Talk to you all very soon.